Section 14.2, area of polygons and circles. So far what we had taken a look at is we had taken a look at kind of measuring the number of squares inside of an object, right? And we broke them down different units. We looked at conversions and how that works out with conversions. But we hadn't actually really looked at any formulas for finding area that would make it easier than counting squares. Agreed? And it would be nice if we had some formulas we could use so we don't have to count squares or draw a picture to count the squares. So we're going to take a look at some basic ones first. And we are, one more, there we go, area formulas. So the first one we have is the area of a rectangle, which you probably remember that one. That one's one that people tend to remember quite well. The area is length times width. Area of a parallelogram is almost the same kind of a formula. It's base times height. You could actually call the area of a rectangle base times height as well. Height is always the perpendicular distance between the bases. So you see the slant of the parallelogram there, but the height is that perpendicular distance. So if you take a look back up the area of a rectangle, the reason that you don't have to worry about it is because they are perpendicular distances already, right? The base would be the length of either the top base or the bottom base because they match. Agreed? So it doesn't matter whether you're measuring the length along the top or the length along the bottom. And then an area of a triangle, I don't have a picture in here because I was going to actually draw one for you. The area of a triangle is actually 1/2 the base times the height. In many respects you could call it the area of a parallelogram cut in half. And it works really just like that. So if you take any triangle that you would like, let me actually draw one in here. So let's say that this is your triangle, and I've purposely tried to draw it so that it doesn't look like it's equilateral, isosceles, or right, or anything specific. It's just a generic triangle. And if you were to measure, or if you were to create the parallel lines to two of the three sides, so like if you were to measure and you were to create this parallel line, and you were to create this parallel line right here, then, again, this is not a perfect picture. Let me try it a little bit so we can get a little bit better. That's pretty good. So if I had drawn it, perfectly, so to speak, these two would be parallel, and these two would be parallel. What you would end up is you would end up seeing that the two triangles, and you could actually prove that the two triangles are in fact congruent, which means they would have the same amount of area because they'd be identical, just in different locations. So it's half of what the area would be for a parallelogram. That's where that comes from. Okay? So, of course, we're going to do some examples. First example, interesting picture. It's actually a bunch of different triangles drawn in there. And it tells you, suppose that we know that line L at the top is parallel to line AB at the bottom. What does this tell us about the areas of all of these triangles that are drawn in blue? So they all have the same AB at the bottom, and they all have different locations at the top, P through U, that they are having as their third angle or their third vertice of their triangle. What would this tell you if you were calculating all of these areas based on the area formula on the previous slide? Who's talking yes? Yes, thank you, Jamie. Say it louder. All those areas are the same. Because what do we actually measure when we have to find the area of a triangle? Well, the base. They all have the exact same base, AB, right? And we measure the vertical height that's a perpendicular height. And the perpendicular height, the one that's drawn in here to look the most convincing anyway, is the perpendicular height would be AQ. Right? And if it's not, there's going to be a perpendicular height in here somewhere. I don't care where it is you mark it. The distance from that top line L to the bottom line AB is the same for every single triangle, correct? So the height of every single triangle is also the same. So since they have the same base length and they have the same height, all of their areas are the same, which is interesting because they don't really look like they would have to be, right? But we could draw those parallelograms just like we established on the previous slide, and we could prove that they are in fact the same. So the areas are equal. And this is like exclamation points because it's like shocking. Oh my word, that's just craziness, right? Yeah, the areas are all equal. Okay, so let's take a look then at another one. This one you are probably not as likely to know. The area formula for a kite. This is a fun one. The area for a kite is 1/2 diameter 1 times diameter 2. I didn't mean diameter, diagonal. Sorry, let me get the right word in there. Diagonal 1 times diagonal 2. And the first picture, of course, is the picture of the kite that you recognize, and love, so to speak, whatever. And then what we've done in the second picture is we have adjusted it. If you will, we've moved, say, this triangle up here, so it goes right there, and this triangle on the bottom up here, so it's matching up here. So we have triangles 1 and 2 on the left, we have triangles 3 and 4 on the right. And the diameter, I think he's still saying diameter, the diagonals are actually cut in half. So if you look at this length right here, this is half of a diagonal, right? The whole diagonal went, I need another color. The whole diagonal went right here. So this is half of that length right there. And then the whole diagonal on the other piece went through here. So we only end up with that, well, we do end up with that whole diagonal right here, right? It doesn't change. So the piece that was halved in this sort of description was the second diagonal, D2, the one that I talked about first. And so it's half as tall as it was before. And we have two rectangles then, right? And the way we measure the rectangle's area is length times width. So the length is D1, the diagonal 1, and then the width is half of what the diagonal 2's width was. So we're turning it into rectangles and we're using what we already knew. Area of a trapezoid, you might remember this one. This one's a little bit more common than the area of a kite. This is 1/2 times the height times base 1 plus base 2. And this is how your book presents this formula. This is not how I think about this formula, so let me show you how I think about this formula, just in case it helps you to think about it in a more clear way. I think about this as base 1 times base 2 1/2 times the height. And here's why I think about it that way, or at least why you can justify that it makes sense from that way. The height is just like having base times height of a trapezoid, or of a parallelogram, or length times width of a rectangle. So there's the height that's in there. You see the height is the vertical distance from the top base to the bottom base. And then what you're doing when you're taking B1 plus B2 divided by 2 is you're averaging them. Right? That's how we average two values together. We add them together, divide by 2. And that's what we're doing when we take our top base and our bottom base, is we're adding them together and we're saying, well, what's the average length of the bases? And that's what you're doing when you see the average there inside of that formula. The next one is very interesting. So let me let you write all the details in and then we'll talk about them. So this is the area of a regular polygon with n sides. And obviously the picture that's drawn is a hexagon. It specifically has 6 sides, but it works for any polygon that's regular. What does regular mean? Let's just clear that up and remember first real quick. Equilateral and equiangular. Okay, so fill in all of the details that are underlined first and then we'll chat. Yeah, A is the apothem, which is marked right here. Okay, that did not show up at all. Let me try that one more time. The apothem, which is marked right here, and then S is the side length.
Oh.
Yeah. So it didn't actually spell out what S was, except that it's referencing the picture. Okay, do we all have them written in at this point? Excellent. Okay, so the first thing to make note of is that we're taking whatever the polygon is, whether it's a hexagon or a pentagon or a decagon, and we're dividing it into that many, the side length number of triangles. And they're all going to be congruent, and the reason we know that can happen is because we're dealing with a regular whatever gon we've got, a regular decagon, a regular hexagon. And then what we're going to do is we're going to use what we know about areas of triangles. If all the triangles are congruent, then we should be able to find just the area of one of them, right? And then multiply it by the number of sides. That's the idea. So if we take one of these little triangles, the apothem, which is the height of the triangle, goes from the center of our n-gon, whatever the gon is, the polygon, down perpendicular to the other side. And it does cut it into two equal pieces as well. You'll notice that it ends up looking like I have an isosceles triangle there that's cut into two equal pieces, which you do. The area of each triangle is 1/2 the apothem, the height, times the side length, s. So we end up getting the area of, say, this one, keep changing into white, into the area of this triangle right here. And then we multiply that by the number of sides of our triangle. 5, or 6 in this case, because I have a hexagon drawn on my screen. So I would have 6 times 1/2 as. Okay, 1/2 base, which is s, times the height, which is a. And then they talk about if you take a look at taking this n times the s, well, n, that's the number of sides of the polygon, times s, the side length, is just the perimeter of the polygon and the distance all the way around. So p equals sn, right? So it's this perimeter is the side length times the number of sides. So there's really two different formulas here that you could use. One of them says that the perimeter of the whole thing, I'm sorry, not perimeter, the area of the whole thing, let me write down right. The area equals n times 1/2 times a for the apothem times the side length s. The other formula says you could just do 1/2 of the apothem times the perimeter of the triangle, of the polygon. So these are the same formula, they're just expressed or thought of slightly differently, and you can use either one of them. Whatever sort of makes the most sense to you is fine to use. Okay, so we've got several formulas that we've developed at this point, most of them based on triangles, right? Broken things apart in either triangles or rectangles and used what we know about those. All right, so we're going to do 3 examples of polygons. So the first polygon picture is a picture of a what? Triangle. So what is the basic formula for a triangle as we're getting started with this particular example? 1/2 base times height. So in this picture, what is the base? It's 5. So the triangle itself is the one that's sort of darkened on your paper. Let me use a different color than the color I've got on here right now. This is the triangle we're trying to find the area of. The base is the bottom part BC, and that is 5. What is its height? Its height's actually 3, and you'll notice it looks and feels a little bit funny because the height's actually measured outside of the triangle. But that's simply because the triangle is oblique. That always happens with an oblique triangle, or not always, but on one of the sides of it, it will happen on an oblique triangle. So it's measured outside. Doesn't matter where it's measured. It measures that it goes from the third vertice straight down, perpendicular to the third, to the opposite side. Okay, so this one was 3. So what do we get if we mark this, or measure this, multiply this out? What do we get? 7, what was it? 7.5, 7.5, and then what are my units? Meters squared, and I'm so glad you guys said meters squared, right, or square meters is how we actually read that, because it's an area measurement, not a linear measurement, so we have to have square units. All right, what's the next shape? It's a trapezoid. So I gave you 2 sort of variations of the formula for a trapezoid. I'll use the one that your book has. It's a 1/2 base 1 plus base 2 times height. So what are the bases of this trapezoid? 10 and 14. How do you know that they're 10 and 14 and not 7 and 9? I didn't actually spell this out. Yeah, thank you for identifying that, because I didn't mention it before. But the bases are the sides that are parallel. So these are my bases because they're parallel sides. How do I know they're parallel? There are no parallel markings on here. Yeah, their right angles here actually tell me that I've got parallel lines, because one of the features and ways that you learned about parallel lines is that things like alternate interior angles are congruent, corresponding angles are congruent. You guys remember doing those? Yeah. So we can talk about that because these are, in this side, they're actually same side interior. But what we have here is that if I pulled this line and continued it on both sides, because this one's 90, so is this one, right? So I automatically get a 90-degree angle here. And then you'll notice that this one being 90 and this one being 90 means that alternate interior angles are congruent. And when alternate interior angles are congruent, the lines are parallel. So we got that. We have that feature in this particular picture. What is the height? 7. Why is it 7 and not 9?
Because 7 is the shortest distance out there, 9 is slanted.
Right. Shortest distance is a good way to think about it. You can also think about it as perpendicular distance. Those are just different ways of saying the same thing. But you need the shortest or the perpendicular distance, not a slanted distance, right? Okay, good. So if I take 10 plus 14, I get what? 24. So what's half of 24? 12. So this becomes 12 times 7. You don't necessarily have to write the 12 times 7 down, but you can if you'd like. Does anyone know what 12 times 7 is? It is 84. 84 what? All right, square centimeters would be our area for this shape, for this trapezoid. All right, I left this picture in here to be as exactly like it was presented in the resource that it came from, because I want you to first understand that the way that they've actually drawn this in here is a very ambiguous drawing. Okay, what's ambiguous? Ambiguous means difficult to understand, or it's not clear. What's ambiguous about this picture?
The markings, you don't know if the 8 is just that side of the other intersection or the whole line.
Right. I mean, because of the way that they've written it down, it's difficult to know, is this 8? Or is this piece 8? They don't mark it, right? So when I create your pictures on your test, when you have them for me on a version like that, I'll be clearer than this particular book representation was. We're going to go with the second one that I marked, that length is 8. The reason we are is because if the shorter length is 8, we have no way to finish the problem. We don't have enough information given. And we're going to do the same thing for the length of 6 right here. We're going to let it be the length all the way across. So we're going to say that this diagonal, it goes like this, that's my 6, okay? So there's nothing in this problem that tells us that. We just have to use that information and assume and hope that's correct, otherwise we're not going to be able to finish the problem itself. So that's what we're going to go with for the particular problem we've got. So what is this a shape of again? A kite. And what's the formula for the area of a kite? 1/2 times d1 times d2. And the d1 and the d2 are in fact the numbers that they gave us with our sort of nuanced, we decided what we wanted it to be on top of that a little bit, right? So what is 6 times 8? 48. And 1/2 of that is? 24. And 24 what? Yep, square centimeters. All right, and we could do pictures all day of different types of polygons, and they all boil down to the formulas that we've been using. I didn't have an example, I suppose, of this one. The formula is used the same way, though. You just need to know the apothem and a side length, or the perimeter would be fine as well in the apothem. All right, now, not polygons. Circles are not polygons, right? So the area formula for a circle is pi r squared. And then the sector, a pie-shaped section of the circle, like a pizza slice, a cake slice, pie slice, can we also have the area found for it. And it looks very much like when we found arc length, right? The edge, I did pizza crust when I was talking about it with you. It's theta divided by 360, this piece right here. Right, that gives you the proportion of the circle that you're talking about. Theta divided by 360. And then you take that measurement times the pi r squared. And if you want to write them where everything's on top of everything on bottom, it ends up being theta pi r squared over 360. This is a little sloppy. It may have been me typing it in, but I don't think so. I think I used it from what I had had it before. These actually should have degree measures on them. Technically, it's all in measures and degrees. So that's how we'll be measuring always in this particular class. So. All right, let's do some examples. 2 examples, in fact. I have used this area formula before in a nutrition context. So I had a situation where I was trying to find out probably the number of calories in a slice of pizza. And the measurement was done, and how I did it was based on the number of slices in the slice and the piece of, or in the pizza itself, and the angle measure that gave me, and all of those pieces of information, and I was able to calculate the amount of calories, approximately, of course, assuming they put everything on there exactly like their website said they would, right, in that slice of pizza. So you can actually use that, and that's how they would have calculated the measurements and some of these things. So let's take a look at this arc, this sector, rather, and finding the area of this sector. So the area formula takes the pi r squared, and it takes the angle measure divided by 360. So what is the angle measure in this sector? 60 degrees. We have pi. What is the radius? 4, and it is centimeters. I leave my units off usually till the end. You are welcome to put them in during the process, so if that helps you more. And then we'll be dividing by 360. All right. I'm more than happy for you to actually take a look at this and use your calculator to do it. There's nothing wrong with that. It would be useful to notice that, of course, the degrees are going to cancel, right? And you might also recognize the 60 and the 360 would, in fact, reduce pretty quickly to having this pi here, and I'll put my 16 in a minute, over 60. Because 60 times, over 6. 60 times 6 is 360. And then the 4 is actually a 16. So that's not a finalized version of something, but you might actually notice some of those cleanups along the way and do them before you put them in your calculator. You don't have to, but you might, right? So what is 16 pi divided by 6?
8.38, we rounded off to 2 decimals.
Is that what you guys got? I've got an error in my notes, so that's why I'm asking. It's okay? 8.38. What are my units here? Centimeters squared. Any questions on that one? That's the area of this piece of pie, this piece of cake. All right, this is a fun one. This would be something like the area around a track field. Not the area, but the area inside of a track field. If you were, you could also find the circumference around the track field, right? But this one is finding area. So if you wanted to know how much space you had or the area you had inside of the track field, around or inside of a football field, inside of something like this, a arena for basketball, something. What would we need to do for this one?
Well, what I would do is you can create one big rectangle
Okay.
inside there with 2 semicircles on the outside.
So something like this is what you're envisioning, is that right? Does everybody see what he's thinking about when he did that? That's how I think about it too. If we chop off the ends of it, we actually have a rectangle in the middle and we have semicircles on the ends. So in a very real sense, we could find 3 separate areas, or we could talk about it as being 2 separate areas, but we could find these 3 separate areas and we could add them together. So in some sense, you could find the area, we'll call it number 1, number 2, and number 3. So we'd have area 1 plus area 2 plus area 3. But you might actually just say that there are 2 areas, and I think that's what Brendan was suggesting. What did you think about with Brendan to consolidate this a little bit cleaner?
Well, you could just do, well, you know what the height and the width by the length are of the inner rectangle, that it's 20 times.
Okay, so this is length times width. It's the rectangle inside.
Right, it would be 20 times 60.
Mm-hmm. And I'll do that in a second.
The diameter of those circles is 16 because the radius is 8.
Okay.
So that would give you the area of the inner rectangle, and then all you'd have to find is the area of one circle because you have two semicircles.
That's what I was wanting you to get to, actually. These two circles are semicircles, right? But if you combined them together, they would be a whole circle. Agreed? So what you really have here, another way of writing it, is you have the area of a circle plus the area of a rectangle. Does everybody see that? So in a very real sense, this is pi r squared plus length times width, and then we can find the different values based on the image that we were given. So since I wrote my circle first, let's do the circle first. What is the radius of the circle?
8 meters.
Yeah, so we've got pi r squared, and r is 8. So that's my circle. It's from down here. And then what would I need to do for the length and the width? That's what you were talking about, Brendan, so I'm going to let you tell us one more time. What's the length first?
The vertical.
The length is usually the longer piece.
Okay, so we'll go with 20.
Yeah.
20 meters.
So 20 is the easiest one to see, right? Because it's actually drawn in there. There's our 20. And then your width would be what?
16.
Okay, and how did you get 16?
It's the diameter of that circle, and we know the diameter because we're given the radius.
Right. So 20 is my length. 16, twice the radius, is my diameter, which is the height of my circle, or the width of my circle. So if I clean this up and simplify this but still have pi involved, I have 64 pi plus what? 320 is right. And your book might even tell you in the back of the book on a problem like this, like leave it like this and actually write down meters squared. It might do that. And it isn't wrong, it's just highly unhelpful if you were talking to any real person, right? They're going to look at you like you lost your mind. So I think an approximation with decimals makes more sense when you're actually dealing with contextual length measurements like meters, centimeters, inches, feet, things like that. So if we approximate, if you take 64 times pi and hit enter in your calculator and then plus 320, what do you get? And we'll go with 2 decimals on everything unless you specified otherwise. What do you get?
521.06.
521.06,
Meters squared.
and then square meters, yes. And we recognize that's an approximation. I'm not terribly concerned that you put the approximation sign, but it is more correct to do so, that we approximate that. The 16 came from the radius of the circle. So the radius was 8, which means it's 8 from here to here, and 8 from here to here. So there's my 16. That green on there was a bad choice. Sorry about that. Any questions on that one? All right.